Recording for this meeting has begun.
So again, good afternoon, everybody, and welcome to today's NICR webcast series, Pricing Mechanisms for Managed Lanes. Let me take a few moments to introduce our two presenters today. Our first presenter today is Dr. Mark Burris. Dr. Mark Burris is a professor of civil engineering at Texas A&M University and a research engineer with Texas A&M Transportation Institute. His main area of interest is traveler behavior in response to pricing, particularly congestion or value pricing. He has served in an evaluation and monitoring role for managed and express lane projects around the country. And prior to joining Texas A&M in August of 2001, I thought it was important to mention that he was a senior research associate at the Center for Urban Transportation Research in Tampa, Florida. Our second presenter today is Saiten Biswas. He is a graduate student in transportation engineering at Texas A&M University. He is working as a graduate research assistant with the Transportation Operations Group at Texas A&M Transportation Institute. His primary research interest is in congestion pricing with focus on managed lanes. He loves analyzing large traffic and toll data, and he has worked extensively to analyze price lanes in Minnesota, California, Colorado, and Texas. So with that being said, I'm going to hand it over to Dr. Burris. So Dr. Burris, take it away.
Thanks, Stephanie. And just double check, make sure you can hear me. Give me a yes.
Yes, you're crystal clear.
Great. Okay, so first I want to thank NICR for the opportunity to do this research. They funded something that I've been curious about for many, many years. And that's the two main different pricing mechanisms for managed lanes, dynamic and variable pricing. And also we had the opportunity to team up with the University of Puerto Rico at MNPASS, and that was a great teaming experience. So I want to mention that they were part of our team that looked into this question of the two pricing mechanisms for managed lanes. Just listing the folks that worked on it, we had fairly large teams at each location with lots of good ideas from all the members. It was a great collaboration. We're looking forward to hopefully getting another project from NICR and collaborating again. So although we were a team, we did have slightly different research focuses for the two universities. At TTI, we attempted to look at as many managed lane facilities as we could, given our time and budget, and that meant not quite as detailed data that we would look at in our attempt to see the impact of the pricing mechanism on travel in these lanes. At Puerto Rico, they had amazing detailed data on one of their facilities, PR22. That's a really interesting managed lane that they have there. And they started their work a little bit after us. So they're not quite finished yet, but hopefully we'll have a future presentation from them on what they found with their managed lane and pricing on it. So a little bit of background for those not as familiar with managed lanes. We've got about 53 of them going right now, priced managed lanes in 11 states and Puerto Rico. And our focus on this, for this project, are price managed lanes. The most common type of managed lanes are HOV lanes, and those require travelers to meet certain occupancy requirements to travel on the lanes. We were focused on the priced managed lanes that require travelers to pay a toll to use the lanes, because we were interested in how the two pricing mechanisms were able to guarantee or at least deliver premium service on those price managed lanes. The image you see here is of price managed lanes in Austin. In the center, you'll see one lane in each direction. Those are the price managed lanes. You have to pay to travel on those lanes. And the outside lanes, 4 lanes in each direction, are what we call general purpose lanes. 3 to 4 lanes in each direction are general purpose lanes, and those are toll free. The price to travel in the managed lanes, the goal of that price is to maintain a premium service on those lanes, better travel speed and travel time reliability on those lanes. So to ensure this premium service, the price has to change based on demand. Now, that can be done in one of two ways. The price changes based on the time of day and the day of week in a set schedule. And we call this variable pricing, and a good example is State Route 91 in California. And this is an image of State Route 91. And here the price increases during periods of the day of increased demand. For example, here for Wednesday at 6 in the morning, the price is $5.15, but if you're in the wee hours of the morning, it's $1.70. And that price is known in advance, set in advance, but it does vary based on what time of day and day of week you have, all in an effort to ensure the managed lanes are providing a premium service. The other option for pricing is dynamically changing that price based on current real-time traffic congestion or traffic conditions. And we call that dynamic pricing. And a good example of that is here on I-35 MNPASS lanes in Minnesota. The tolls can range anywhere from 25 cents to $8 and can change as often as every 3 minutes based on traffic densities that are calculated every 30 seconds. So as the traffic density changes, so does the price. And if you have very rapid increases or decreases in traffic density, you'd have rapidly increasing and decreasing toll prices. So those are the two methods of pricing these managed lanes. There's some that have a hybrid when they just start, but typically it's either variable pricing or dynamic pricing. And the focus of this research is which one is better? Is there a clear winner and one you should be picking when you look to start up and operate managed lanes? Well, in theory, you can really argue that dynamic pricing should be the best. You're reacting in real time to real traffic conditions with that price, and with variable pricing, you're setting that price in advance, and at any given time, traffic could change dramatically from typical, and you couldn't react to that change. But there are some disadvantages. One, it's a more difficult sale to the public and the politicians that you're going to have a toll lane, but you're not going to be able to tell people what the toll is in advance. They can only see it as they travel towards the toll lane and they see it on a sign. You don't know it days in advance. You also need more equipment and being able to have some algorithms taking in a lot of traffic data to adjust that toll in real time. So it's not near as easy. You need a lot more equipment and algorithms, but also based on some of the research I've done, we're seeing an awful lot of the people traveling on these freeway facilities that are relatively insensitive to price. They pick a lane, a type of lane that they like. For example, they always use the general purpose lanes, and they stick to those. And it really doesn't matter what the toll is or the travel time is, the travel time savings is, they stick to those lanes. So with all that background and the success of many of the variable price facilities, I had been curious for many years is all the extra effort of putting in dynamic pricing, is it giving you a superior product? Is it worth it? And finally, through NICR, had the opportunity to dig into that. But we needed to figure out how to measure the ability of the toll to provide that premium service. So we had to come up with some performance metrics that were easily measured and contained travel data that was being collected already. They had to be meaningful to both the travelers and the toll authority, and they had to be performance metrics that the toll would have an impact on. So we needed to figure out what performance metrics we could use that would really tell us, is this toll doing what it needs to do to maintain a premium service on the managed lanes? And we used those performance metrics on both dynamic and variable price lanes and see which ones perform the best. So again, we tried to do as many lanes as possible, but with each and every lane we attempted to do, there was always some issues with the data, and nothing was easy. So in the end, we managed to compare and measure the performance metrics for 6 different lanes. Here we have 4 that use dynamic pricing and 2 that use variable pricing. And that ratio is not really a surprise. There's a lot more managed lanes out there that use dynamic pricing than variable pricing. So what performance metrics did we land on? Well, no surprise, the first one is travel time savings. That's a key metric for the users, the travelers, and why they would want to pay the toll rate. We simply took the travel time on the general purpose lanes minus the travel time on the managed lanes. And we would do this for any time the managed lanes were open. And this goes across all of the performance metrics. We wanted to do our best that we could to measure what the average managed lane traveler experienced. So we looked at all time periods that the managed lane was operational and charging a toll, and we weighted our results based on the volume of traffic in the managed lanes, so that the peak period where the managed lanes have a lot more travelers would get weighted a lot heavier than off-peak or overnight periods where the managed lanes had very, very few travelers. So the overarching goal is our final travel time savings that we present is what the average managed lane user experienced. Similarly, with the reliability benefit, we looked at the standard deviation of travel time on the general purpose lanes divided by the managed lanes. And in theory, you would have a much larger variability or standard deviation of travel time on the general purpose lanes, and thus the managed lanes are a greater benefit to you because they're more reliable. So as the reliability benefit number goes up, that means the managed lanes are offering you more and more reliability as compared to the general purpose lanes. So for both of these metrics, a larger number is better for the managed lanes. And for all of these metrics, we'll see that. The larger number means the managed lanes are doing better. A similar metric to the reliability is a planning time benefit. And the planning time index is defined as the 95th percentile travel time, or one of the worst travel times, the worst travel time out of 20 trips, divided by your free flow travel time. So that looks again at variability with a focus on the worst trip. And it's called a planning time index because if you want to plan to be on time to your destination 95% of the time, then you need to plan for that much travel time to be sure you arrive at your destination 95% of the time on time. So we took the difference of planning time indexes on the two lanes as our next performance metric. And again, higher number means better for the managed lane because you want a really low number here. A low number for your planning time index indicates there's not much variability and your 95th percentile worst travel time is really close to your free flow travel time. And those are from the perspective of the traveler. We also looked at the perspective of the toll agency. And for many of the express lanes out there in the country, they have a speed requirement from the FHWA that at least 90% of the time in the peak, they reach 45 miles per hour average travel speeds. So we thought that's an important threshold that the toll price must be able to maintain traffic conditions at least 45 miles per hour or better in the peak. And several of these managed lanes also had owner-specific goals, such as maintaining 50 miles per hour in the peak or in the entire day. So we looked to see if they accomplished that based on our travel time or speed data. We also wanted to see that visually, so we developed these graphs that look at how speeds vary on the managed lanes and general purpose lanes. And this next graph is an example of that. We made the center of the graph 45 miles per hour in both lanes. The y-axis is the speed on the general purpose lane. The x-axis is the speed on the managed lane. And every time increment, and it would depend on what data we had, but let's say we had data in 1 minute increments, then the average speed on the managed lane and the general purpose lane in that minute is represented by one dot on this graph. So for example, if I just randomly pick a dot here, oh, the draw tool didn't work so good. Hopefully people see an arrow now. I think I've got an arrow on there.
You do.
So
Yes, you do, Mark.
Okay, good. So if I pick that random dot, that's telling me at that minute, the general purpose lane speed was 55 miles per hour, while the managed lane speed was maybe slightly less, 53 miles an hour. So we plotted this for all the data we had for each of the facilities, and any speeds above 45 miles per hour on that x-axis, that's achieving that FHWA goal. And in this case, we see it's really close to the 90%. It's 85% plus 4.5%. And any speeds above the 45-degree line going right through the graph would indicate that the general purpose lanes would be faster. Any dots below the 45-degree means the managed lane is going faster. And it gave us a feel for the travel speeds out there and if we were accomplishing our goals of having fast lanes. We also attempted to do something that was similar to elasticity. We attempted to look to see if the impact of the toll on congestion. So we would look at the volume of vehicles traveling at a given toll rate and say that toll rate is $4 to $6. So anytime there's a toll between $4 and $6, we get the number of vehicles traveling on the managed lane. And then for every time that happened, we would take the average. So there might have been an average of 1,000 vehicles traveling at any given toll rate between $4 and $6. And we do that for all the different toll brackets. We'd get an average number of travelers in the managed lane, vehicles in the managed lanes for that toll bracket. And then we'd see how that changed as the tolls increased from one bracket to the next. In typical elasticities, you'd expect as the toll price to go up, the volume of vehicles to drop. But that's not necessarily so on managed lanes. In fact, it's kind of the opposite for managed lanes, where as your volumes on the managed lane increase, your whole goal is to increase that price and make sure volumes don't exceed the capacity of the lanes. So this was a metric to try and see if the price, especially at the higher levels, was able to keep traffic in line and not going over the capacity. And our last one, our scoring index, was the same idea. And this one we developed specifically for this project, measures how well the managed lanes are doing compared to the general purpose lanes in flow and speed. And we would do this, if we had 5-minute data, we'd do this for every 5-minute increment. And to explain this, first we would look at things like the speed flow of the lanes. Let me get back to speed flow. We look at the speed flow graph and maybe a volume density graph of the lanes and try to see where the capacity of the lanes would lie. And this one might be around 1700-ish, where speeds and flow would go good up until about 1700. Once you pass 1700, you start seeing breakdown of traffic and congestion occurring and slower speeds. So for that particular lane, getting up to and around 1700 vehicles per hour per lane would be a good goal. You get a throughput like that, you're achieving your objective if you're doing that at high speed. So we developed this flow chart to score each lane in each 5-minute increment. To start with, you had to have some flow in the managed lane, or we just gave it a score of 0. So those overnight times probably have a score of 0. And then we looked at the speed of the managed lane in that given 5-minute increment. If the managed lane was flowing very fast, we'll go down that side of the chart. If it was traveling at greater than 55 miles per hour, we would then look at the managed lane flow. If the flow was greater than or equal to that capacity, that means we have a lot of vehicles traveling very quickly on the managed lane. That's going to give the managed lane a high score. If the general purpose lane was actually congested and speeds at less than 45 miles an hour, that would give our managed lane the highest score of all, a +3. If the general purpose lane was also operating pretty good, you'd get a +2. The exact opposite occurs on the far end of this chart, where if the managed lane is slow and not moving its capacity, plus the general purpose lane is flowing actually better than the managed lane, we would give the managed lane a score of -3. So we'd go from +3 to -3 for every minute the managed lane was open to give it a score based on how well it's operating. And with that, I'll turn it over to Saitan to talk about a couple of specific examples.
Yeah, so coming to the brief description of the dynamically priced facilities. So first we have the MNPASS express lanes in Minnesota. So as you can see from the figure, there are currently 3 MNPASS express lanes, the I-35 West, I-394 and the I-35 East. So for each of the managed lanes, there is one managed lane in each direction, and the general purpose lanes vary depending upon 2 to 4 in each direction. Also, the traffic data was extracted from the Minnesota Department of Transportation data extract tool, which is an open source thing available online, and we have extracted it at 3-minute granularity. Also, a fact about the lanes is that they operate only on weekdays, and that too in the peak hours, which is 6 a.m. to 10 a.m. in the morning and 3 p.m. to 7 p.m. in the evenings. Also, we got the data for the entire year of 2016 and 2017. Also, the tolls data was genuinely shared by the Minnesota Department of Transportation to us, and the tolls can range between 25 cents and $8 and can update every 3 minutes depending on the speed and the number of vehicles using the lanes and the change in the traffic density at the most congested downstream segment. So next, I have a brief map of the I-35 West express lanes here. So here we can see that the express lanes start from the city of Burnsville, and it connects to the downtown Minneapolis region. And we can see that the northbound lanes and the southbound lanes here. So the northbound lanes are a bit longer compared to the southbound lanes. And the important thing to note here is the tolling location, which is shown by the yellow place mark. So these are the locations where we obtained the toll transaction data from the Minnesota Department of Transportation. And basically we have multiple detectors, around 15 to 20 in each direction, and we obtained the speed and traffic data from there, and we average the speeds to obtain the travel time at each time granularity to obtain the final performance metrics. Next, we also have the I-394 express lanes here. So the I-394 express lanes were basically the first express lanes to operate in Minnesota, and the lanes are basically 11 mile long, and it connects the city of Wayzata, here we can see, and to the downtown Minneapolis area. So an interesting thing about this facility is it is made up of two sections. One is the concurrent flow sections from Wayzata Boulevard to the Xenia Avenue, and next after that we have a reversible section. So basically for our analysis we have considered times only when both the sections are available to use by the traveler, and we have assumed that a traveler uses the entire length of I-394. So basically it reduces our analysis to the morning times, which is 6 a.m. to 10 a.m. and in the evening from 3 p.m. to 7 p.m. And similar to the previous facility, we can see here the tolling locations. So they are basically lesser than I-35 West, but yeah, this is how it looks. Also, we have another facility which is I-35 West, and it is the newest facility in Minnesota, which opened pretty recently in 2015 and 2016, part by part. Next, for another dynamically priced facility, we have the MOPAC express lanes. So basically in the figure we can see the MOPAC express lanes start near Caesar Chavez Street and go up to Palmer Lane. So they are located in downtown Austin, and it is basically 11 miles long, and there is 1 ml and 3 general purpose lanes in each direction. And similar to the Minnesota data, we obtained the data here from the Central Transportation Regional Mobility Authority, and they provided us the data in a similar format at 4-minute granularity intervals. Also, the data was available for the entire year of 2018, so it was pretty neat data. And there are 3 entry and exit locations, as we can see here, one at the start, one at the end, and one middle way right at the middle, which is known as RM2222. So basically, in a nutshell, we have 4 dynamically priced facilities. Now, considering the variably priced facilities, we have only 2. So on my right, I have the I-25 North Express lanes in Colorado. So these lanes are relatively very short. They are only 6 miles long, and similar to MOPAC, we have 1 managed lanes and 3 general purpose lanes in each direction. However, the traffic data was obtained at 1 hour granularity intervals from the Colorado Department of Transportation, and also the toll data was openly available online because it's a variably priced facility. However, the data was only available for 4 months from January to April in 2019. And on my left, I have the State Route 91 express lanes in California. It is one of the most popular express lanes throughout the United States, and it was the first one to begin operations. So basically the lanes are 18 miles long, and it always has two managed lanes in each direction of travel, and the general purpose lanes are vary from 5 to 6 in each direction, so it's a huge facility. And the data is available online from the Caltrans website, which is widely known as PEMS. And we obtained the traffic data and as well as the travel time data at 5-minute granularity from the website. And also we extracted the data for entire year 2019, and the tolls here basically change by hour, so it is a different toll in the morning hours and it can change each hour. Also, for the facility, the HOV 3 Plus is free most of the times throughout the facility, except in the eastbound direction in the evening peak from 4 p.m. to 6 p.m. So here basically we can see a brief map of the State Route 91 express lanes. So we can see that the lanes start near the State Route 91 and I-55 interchange, and it ends near the ends after the Riverside County near McKinley Street. And basically there is only one major exit, which is right at the midway at the county line. And basically we have only analyzed the data from the Orange County. This is primarily because the data from the Riverside County looked a bit erroneous, because the travel times in the general purpose lanes appeared a bit shorter than the managed lanes, so we did not use that data. So we only had the Orange County data for the year 2019. So basically, as Dr. Burris also discussed, we total have 6 facilities, 4 dynamic and 2 variable. So here I have just shown a sample results for the Minnesota part. So here we can see there are the 3 facilities marked here, and for each facility we have some different routes. So for example, for I-35 West we have 4 different routes, for I-394 2, and for I-35 East we have 3 routes. So basically the next column gives us the length of the segments, just to get a brief idea. And coming to our metrics, first we have the travel time savings. So we can see that the travel time savings vary a lot, starting from as low as 0.4 minutes to as high as 2.5 minutes. Next, we have the reliability benefit, which was discussed. It's the ratio of the standard deviation of the travel times in the general purpose lanes to the standard deviation of travel times in the managed lanes. So basically a higher value indicates that the managed lanes are more reliable and the general purpose lanes have a higher standard deviation. So here also we can see the values can range from as low as 0.5 and it can go as high as around 2.3. The other metric is the planning time index benefit. So it basically tells us how worse the managed lanes are performing on the worst day. So here we can see like the travel times on the managed lanes can go up to 1.66 times the normal ones, and it can be as less as 1.08 times. So basically this is the planning time index for the managed lanes, and similarly we calculated the planning time index for the general purpose lanes, and we took the difference of the planning time index of the general purpose lanes and the managed lanes, and we observed the values. So a higher value indicates that the managed lanes are performing much better than the general purpose lanes. Next, we have the speed graphs, as was discussed by Dr. Burris. So basically this is just a sample graph for the northbound and the southbound segment for I-35 West. So basically the center of the graph is at 45 as per the FHW speed standards, and here we can see like any point on the first quadrant and the fourth quadrant is good for the managed lanes in general, because the managed lane speeds are better than the general purpose lanes, and anything on the second and the third quadrant is worse for the managed lanes. And here we can see like very few, around like 1.55% lies for the northbound segment here, and around similar numbers lie for the southbound segment here. And basically the first quadrant is good for the entire facility. It's mainly because the managed lanes are performing greater than 45, and so are the general purpose lanes. So here we can see a high number, 85% and around 94% here. But on the fourth quadrant, the percentages here show that the managed lanes are performing really good while the general purpose lanes fail to achieve the 45 mph criteria. So here we can see like roughly it's a good number. 14% of the cases the managed lanes are better than the general purpose lanes here, and while it's only 5% here. So basically this graphs gives us a quick visual of how the managed lanes and the general purpose lanes are performing. Next is the scoring index and the speed criteria. So as discussed, the FHWA goal is to maintain 45 mph at least 90% of the time during the peak periods. So here we can see it does, the MNPASS facility does pretty well. So it's almost like average 98% of the times the managed lanes are better than 45 mph. Also the MNPASS lanes have an internal goal, like they have to maintain 50 mph all the times. So here also see it does really well, like on an average 95% of the times it matches the goal of the facility. Also, the other thing is the scoring index, which was also explained by Dr. Burris. So here I have just shown a sample for the I-35 West. So the northbound weighted average is 0.72 and the southbound is 0.8. So it's expected that it's close to 1. And these are again weighted by the volume of traffic in each of the directions to obtain an overall score for the entire facility, which will be discussed at the last by Dr. Burris. So here I have shown a brief description of the scoring index. So this scoring index is calculated at a particular representative location, which is known as Cliff Road in I-35 West northbound direction. So basically here I am showing that the number of times the raw score has been obtained from -3 to +3 in increments of 1. So as we can see, the maximum amount of times the score is 1, which is when the managed lanes are performing good and the general purpose lanes are performing good too, and also the lane capacity of managed lanes is greater. And also we can see the negative scores, we have obtained very less negative scores, which is also evident from the speed flow graphs. And next we have summed up the total ML flow at each of the distinct scores, and later we have taken a weighted average to obtain the score for the particular location. Here it's coming as 0.92, which is a good value, and if it should not be negative for sure, and if it is a lot high, for example if it goes to 2 and above, it tells us that the managed lanes are performing good but the general purpose lanes are failing, which also we don't intend to observe from using the managed lanes. So after obtaining this score of 0.92 at a particular location, we have done it for multiple locations around 7 to 8, and we have weighted it again by the volume to obtain the overall score for each facility. Next is the ability of the toll to impact congestion metric. So here I have considered the toll intervals to be 1, so it's like $0.25 to 1, and it goes on. So there are 8 distinct toll intervals, and we have used a weighted average to find the toll for the particular toll bracket. For example, for the tolls between 0.25 and 1, the average toll comes out to be around 0.75. And we have also taken the average ML throughput. So whenever the toll is between 0.25 and 1, what is the average ML throughput we are getting? So this is basically, it shows this. So next we have just did the percentage change in the average vehicle throughput at different levels, and similar is the increase in toll, and we have tried to measure the ability how the toll is doing in impacting the congestion, which is similar to the elasticity metric. So we can observe that at lower toll intervals, say up to $5, the users are experiencing an urge to use the managed lanes, which is shown by the positive impact up to $5 tolls. However, at higher tolls above $5, from 5.25 to $8, we can see that the metric is coming negative, which tells us that the average throughput is falling in the managed lanes, which is pretty much expected because at higher tolls the users are expected to be discouraged from using the managed lanes. Next, I will turn it over to Dr. Burris once again.
Okay, we're running low on time, so I'll go through the final results here pretty quick. The two variable price facilities, you see here their final scores and how we did that. And I'm sorry, I'm going to jump ahead to get to the overall conclusion. But you can look at these slides and download them. Here's our 6 variable dynamically priced facilities. Again, their overall score. But if we take a look at the average on these two, we see dynamic pricing winning in each category except reliability benefit. And that's a good sign for dynamic pricing, but see here in our conclusion slide, we aren't convinced that that's the final word. We did see both pricing mechanisms are working well. We think those performance metrics we used do a pretty good job of telling us if the toll is working to keep traffic flowing on the managed lane. I say no clear winner, although dynamics seem to be winning. Part of the issue is lack of data on variable price facilities. We just had the two. One of them didn't have many months of data. The other, we're a little suspicious of some of the PEMS data from SR91. So I'm not ready to say there's a clear winner, although dynamic pricing looks pretty good and is winning in most categories. You can always send us questions by email, and Sayatan is also graduating very soon and looking for a job, so he'd be most interested if anybody out there is looking for someone experienced doing managed lanes. And we seem to have jumped over.
Yeah, so Dr. Burris, I did just quickly open up the evaluation. I know we are at the 1 p.m. time, so if somebody needed to drop off, I did want to at least open up the evaluation and give everybody an opportunity to provide feedback about today's webinar. I know we're sort of short on time, but do you have the opportunity to answer the 2 questions that we have submitted in the Q&A box?
Yeah, I think I can remember them. One was about when
I'll read them. I'll read them for you. How about that? Okay.
It was when people make the decision whether or not to use the managed lane, and that is something I've been trying to research myself based on some of the results I'm getting from lanes. And I asked that question recently on a survey for MOPAC users, and we got a pretty even distribution of I pick one lane and stick to it all the time. I choose the lane as I'm leaving the house based on what type of day I'm having, if I'm late and such like that. And a good percentage say I pick it as I'm approaching the lane and I'm looking at traffic around me. So there is no one right time for when people are making this decision. It's all over the place. The other question was, do any of these show I think it was the travel time savings? Is that it, Stephanie?
Yeah, do any of these facilities provide travel time information to the driver prior to their having to decide whether to use the managed lanes?
Mm-hmm. So most of them provide half of the information. A lot of these will be on facilities where the general purpose lanes have dynamic message signs talking about the travel time to upcoming major exits and points. But there are very, very few, I think only 2 I know of in the whole country, that you get to see both the travel time on the general purpose lanes and the managed lanes. And I think there's one in Dallas. I think I-15 San Diego has, but it's really rare that you see both travel times and you can compare them when you make the decision which lane to use.
Okay, that looks like the end of the question. So again, I would like to thank everybody for hanging in there a few minutes late, but that's okay. Again, I'd like to just remind you that our next webinar is actually part of our Friday transportation seminar series that is open for anybody to attend. There is a specific link to attend this seminar, but it is not a registration-based link, but that is provided in the web link section. So if you're interested in hearing about investigating autonomous vehicle impacts on individual activity travel behavior, please create a little calendar appointment and add that to your calendar so that you'll be ready and available for that. So again, I'd like to thank Dr. Burris and Sayatin for presenting today, and we'll see you soon. Bye, everybody.
Bye.
Thank you, Stephanie. Bye-bye.
You're welcome.